Imagine for a second that you've hired this incredibly smart personal assistant. I mean, top of their class, right?
Oh, absolutely.
Yeah.
The kind that can draft brilliant reports in seconds.
Exactly. Like, they can solve these intricate logical puzzles on the fly, and if you ask them to organize your files, they do it flawlessly.
Sounds like a dream.
Right. But there is one massive glaring catch. This assistant is a complete amnesiac.
Oh, wow. Okay.
Yeah. Every single time you hand them a new task, they have absolutely no memory of the last thing they did for you.
So they don't learn your preferences at all.
Nope. They don't learn from the mistake they made yesterday, and they treat every single interaction like it's literally the very first time you've ever spoken to them.
Well, it sounds like a productivity nightmare, honestly. But, you've just perfectly described the underlying reality of most large language models today.
Right, because of the amnesia.
Yeah, exactly. Despite all their vast capabilities at their core, they are stateless. Right. When you close the chat window, the session just dies. They don't naturally accumulate reusable experience across interactions to become, more tailored to you over time.
Okay, let's unpack this, because that stateless nature is arguably the major bottleneck in AI right now.
It really is.
But welcome to today's deep dive, where we are looking at something that completely flips this script.
Yeah, we've got some fascinating sources today.
We really do. We are exploring a groundbreaking new framework called Mem-pi. That's M-E-M-P-I. It was developed by researchers at ServiceNow AI Research, Mila, the University of Montreal, and others.
A really heavy-hitting team.
Definitely. And the mission of this deep dive is to understand how Mem-pi is shifting AI from relying on these clunky, static filing cabinets of memory to a dynamic generative memory.
Which is a huge paradigm shift.
It totally is.
Yeah.
We are talking about an AI that actually knows when to speak up and, crucially, when to just stay quiet.
Yeah, because in a world characterized by severe information overload, true intelligence isn't just about having access to all the data in the universe.
Right. We already have search engines for that.
Exactly. True intelligence is about filtering. It's about knowing precisely what information matters right now for the highly specific context you find yourself in, and just ignoring the rest.
To really appreciate why Mem-pi is such a massive leap forward, I feel like we have to look at the current state of things.
Yeah, we have to set the baseline.
So when developers try to fix this amnesia problem today, how are they actually doing it?
Well, the industry standard approach right now is called retrieval augmented generation.
Or RAG, right?
Yeah, commonly known as RAG. You can think of these as episodic memory banks. The system basically collects fragments of past interactions, stores them in a database, and then...
Oh, so it's just saving text files.
Essentially, yes. And then when a new query comes in, it runs a mathematical comparison. Usually it's vector similarity to retrieve relevant past entries.
Okay, let me try to visualize this. It sounds like current AI memory is basically a literal physical filing cabinet.
That's a really good way to put it.
Look, let's say you ask an AI agent to help you draft an email to a difficult client. Under the RAG system, the agent turns around, rummages through this massive metal filing cabinet of past experiences.
It's digging through old papers.
Right. And it pulls out a piece of paper that shares some similar keywords. Maybe it's an email to a totally different client about a totally different problem, and it blindly hands it to you as a guide.
That analogy holds up perfectly, especially regarding the limitations of the system.
Because it's just looking for keywords.
Yeah, because RAG relies on vector similarity, it's essentially doing an advanced keyword search. The retrieved memories are inherently static. They are literally copy-pasted text from a past event.
Oh, I see.
So the agent receives a hint filled with irrelevant details or instructions that are overly specific to a past situation that doesn't actually align with the user's current reality.
Which feels entirely unnatural. I mean, decades of cognitive science tell us that human memory is not a literal replay mechanism.
No, not at all.
When you remember a past vacation, you aren't pulling a static, unchangeable video file out of a funneling cabinet in your brain.
Right. Memory is a constructive process.
Exactly. We dynamically reconstruct our recollections based on our prior knowledge and the context of whatever's happening to us in the present moment.
And that is the exact cognitive science twist that inspired the researchers behind Mem-pi.
They looked at human cognition.
They did. They asked a fundamental question. If human memory is a constructive, generative process, why on earth are we forcing artificial intelligence to use a static filing cabinet?
So what did they build instead?
Their solution was to model memory not as a storage database, but as a generative policy. Mem-pi is an entirely separate, dedicated neural network.
Wait, let me make sure I'm following. The memory itself is a separate AI.
It is. It's either a language model or a vision language model with its own parameters, completely decoupled from the downstream AI agent that actually performs the tasks.
So it's basically a two-brain system.
Exactly. Instead of retrieving a static text file from the past, this dedicated memory model synthesizes context-specific guidance on demand.
Okay, so it's making it up on the spot.
Yes, it looks at the agent's current situation and essentially hallucinates a helpful, custom-tailored memory specifically designed to cue the agent for the exact problem it's facing right now.
Okay, hold on. I need to push back here.
Sure, go ahead.
If I have a memory model that is literally custom generating hints and it's powered by its own neural network, shouldn't more information always be better?
You would think so, right?
I mean, if the agent is struggling, why wouldn't the memory model just try harder to generate a better hint? Why is abstaining entirely or staying quiet even an option we'd want?
What's fascinating here is that in complex systems, silence is sometimes golden.
Really? How so?
You have to consider what happens in ambiguous, weakly grounded, or totally novel situations, what developers call out-of-distribution contexts.
Like when the AI has literally never seen this exact problem before.
Exactly. If the memory model encounters a problem it has genuinely never seen before, and it is forced to speak, it won't just say, I don't know.
Right. AI hates saying, I don't know.
It does. It will invent a highly confident, plausible-sounding, but completely incorrect hint.
Ah, the classic AI hallucination problem. But in this case, it's hallucinating its own memories.
Precisely. And the downstream agent, the one doing the actual task, inherently trusts its memory module.
Oh, wow. So it's blind trust.
Right. So if the memory module confidently feeds it a hallucinated, incorrect strategy, the base agent will blindly follow that strategy right off a cliff. It actively sabotages the task.
So the system absolutely must possess the self-awareness to know when it's out of its depth.
And that is the true genius of Mem-pi. The architecture actually includes an explicit decision token, simply labeled abstain in brackets.
An abstain token. I love that.
Yeah, the generative policy jointly learns not just what to generate, but when to generate.
It's learning timing.
Exactly. It evaluates the situation, and if it calculates that jumping in would introduce counterproductive noise, it simply emits the abstain token and stays completely silent.
I found a brilliant example of this in the source materials shopping benchmark case study.
Oh, the Nintendo Switch one.
Yes. The task given to the AI agent was to navigate a simulated e-commerce site and find the best storage option to fit all 40 of a user's Nintendo Switch game cards.
A seemingly simple, everyday web navigation task.
Right. But the old retrieval method, the RJ filing cabinet, completely botched it.
What did it do?
It looked at the query and ran its keyword similarity search. It found a past task involving Nintendo Switch games and pulled the static hint from that old file.
And let me guess, the hint was way too specific.
Exactly. That old hint explicitly told the agent to search for the specific terms game card case or cartridge holder.
On the surface, that sounds like helpful, actionable advice.
It does. But by injecting that highly specific hint, it forced blinders onto the agent.
It narrowed the search too much.
Right. It locked the agent's search entirely to a narrow product family. It caused the agent to ignore broader organizers, travel bags, or better storage solutions that might easily hold 40 cards.
So it failed.
Completely. The agent failed the task because it was sabotaged by its own overly specific rigid memory.
And how did Mem-pi handle that same exact prompt?
Mem-pi looked at the task, processed the phrase best storage option, and realized that restricting the search terms to cartridge holder would artificially limit the results.
So it knew the hint was bad.
Yeah, so it didn't try to guess a better search term. It simply omitted the abstain token. It stayed completely silent.
And by staying silent, abstention restored the base agent's open search capabilities.
Exactly.
The agent was free to explore the e-commerce site dynamically and successfully found a much better organizer.
Okay, so we know what Mem-pi does. It generates custom hints. And we know why it abstains. To avoid acting like a backseat driver when it doesn't have a good map.
Right, nobody likes a backseat driver.
True. But how do you actually teach a neural network to make these incredibly nuanced decisions? I mean, deciding whether or not to speak up in a meeting is something a lot of human beings haven't even mastered.
It's true. Training that level of judgment requires a highly sophisticated two-stage architecture.
2 stages. Okay.
Yeah, the first stage is called experience distillation. The researchers took an offline bank of experiences, specifically a database called JEF Hinter.
JEF Hinter.
Right, which contains raw interaction logs that have already been boiled down into compact hints. They take this bank and use supervised learning to compress all those offline experiences directly into the Mem-pi model's parameters.
I want to translate that for a second just to make sure I'm getting it.
Go for it.
When you say supervised learning, we are basically talking about how predictive text works on your phone, right?
Pretty similar concept, yeah.
It's looking at massive amounts of data and learning to predict the next logical word. It's memorizing the textbook to imitate what a helpful hint looks like.
That's a great way to visualize it. It learns the syntax and structure of good advice. But, imitation is a trap.
How so?
The supervised policy learns how to sound helpful, but it has no idea if the hint it just generated actually helps the downstream agent succeed in a live, unpredictable environment.
Right, because sounding confident and actually being correct are two very different things.
Extremely different. Which brings us to the critical second phase, adaptation distillation.
Okay, what happens here?
Here, the model learns from the actual real-world outcomes of the downstream agent using reinforcement learning. Specifically, they use an algorithm called GRPO. That stands for Group Relative Policy Optimization.
Okay, let's break down GRPO because the math behind this is fascinating. How does it work in practice?
Think of the group in GRPO as a batch of attempts. For a single task, the memory model generates a group of different hints.
So it throws a bunch of options at the wall.
Exactly. The downstream agent then tries to solve the task multiple times using a different hint from the group each time. The algorithm then evaluates the relative success of those attempts.
Like, did one hint work better than another?
Precisely. Did hint A lead to a faster success than hint B? If so, the policy optimizes its internal weights to favor the logic that produced hint A.
But wait, here is where it gets incredibly tricky. The system has to learn two completely different things simultaneously, right?
Yes.
It has to learn whether to abstain, which is just one single token. And it also has to learn what to say in the long string of text if it doesn't abstain.
That's the core challenge.
If you lump all of that into one training score, doesn't the learning signal from the massive paragraph of text completely drown out the learning signal for that one tiny decision token?
You are hitting on the exact mathematical hurdle the researchers had to clear. If you use standard reinforcement learning, the system just gets confused.
So how did they fix it?
To solve this, they implemented something called decision content decoupled policy optimization.
Okay, let me try an analogy here to explain this decoupling concept.
Let's hear it.
Imagine you are a culinary instructor evaluating a chef who is cooking a complex dish. You have to grade this chef on two completely separate things.
Okay.
First, whether they decided to add salt to the dish, that's the decision. And second, what kind of salt they chose to add, like standard table salt versus an artisan Himalayan pink salt. That's the content.
I like where this is going.
Right. If the chef decides to add salt to a dish that is already incredibly salty, the dish is completely ruined.
It's inedible.
Exactly. At that point, it doesn't matter if they use the finest Himalayan pink salts in the world. You shouldn't be giving them feedback on the subtle flavor profile of their salt choice.
Yeah.
You should be failing them on the fundamental decision to add salt in the first place.
Yeah.
You have to decouple the decision from the content.
That is a perfect analogy. And if we connect this to the bigger picture of the Mem-pi architecture, the researchers achieved this decoupling by using structured counterfactual rollouts.
Counterfactual rollouts.
Yeah, you can almost think of it as the AI living through the multiverse.
Oh, I love a multiverse analogy.
Right. For every task, the model splits into alternate realities. In one branch of reality, the model is forced to emit the abstain token. In the other branches, it is forced to generate various hints.
So they can directly compare the timelines. They look at the final score and ask, did the timeline where you stayed silent result in a higher score than the timelines where you gave advice?
Precisely. And they use that comparison to implement a mathematical mechanism called delta gating. Delta simply refers to the difference in the reward scores between the timelines.
So if silence wins out.
Exactly. If the stay silent timeline scores higher than the give a hint timeline, the delta is negative.
And what does the system actually do with a negative delta?
It drops a gate. If generating a hint was the wrong move, delta gating literally zeroes out the learning gradient for the generated words.
It just blocks it entirely.
Yes. It blocks the model from updating its content parameters. It ensures the model doesn't waste computational power trying to become a better hint writer for a situation where it shouldn't be writing a hint at all.
Going back to the chef, if adding salt ruins the dish, Delta gating prevents the chef from wasting time analyzing which brand of salt was used. It just harshly reinforces the neural pathway that says, don't add salt here next time.
It isolates the learning completely. The decision tokens learn when to generate by comparing the different multiverse branches against each other.
Right.
Meanwhile, the content tokens learn what to generate only within the branches where speaking up was actually the correct choice.
This level of decoupled training and simulating alternate timelines to isolate variables, I mean, it sounds incredible in theory, but the source material provides extensive data proving that it radically outperforms traditional retrieval methods in actual practical applications.
Oh, absolutely. The testing environments they used to benchmark Mem-pi were rigorous and really diverse.
They really put it through the ringer.
They did. They deployed it in Web Arena, which tests complex multi-step browser tasks like canceling orders on e-commerce sites or managing user permissions in a software backend.
Very realistic task.
Yeah. They used Work Arena, which tests enterprise software workflows like navigating Jira or managing spreadsheets. They also tested it on Lifelong Agent Bench for terminal tool use and ALF World, which simulates embodied robotic tasks in a household environment.
And the results are just wild. Mem-pi consistently outperformed the retrieval-based baselines across the board.
Numbers are staggering.
Yeah, on average, they saw a 20% relative improvement over the base agent.
Oh,
But on Web Arena, which is arguably the most complex and realistic web navigation benchmark, that relative gain approached a massive 50%.
a near 50% improvement just by changing how the memory module operates without altering the underlying base agent's core capabilities at all.
I want to highlight a specific case study from Web Arena because it perfectly illustrates the difference between RIG's filing cabinet and Mem-pi's constructive brain.
Let's do it.
It's the top 3 rewrite case from the content management system domain. In this test, the user asks the agent to list the top 3 search terms in my store.
Okay, and let's look at how the traditional RAG system fails here.
Right. The RAG system searches its filing cabinet using vector similarity. It finds a past task that shares the keywords top search terms.
Okay, seems logical.
But that past task was asking for the top 2 terms. Because a RAG is just copy-pasting text strings, the static hint it blindly hands the agent says, locate the top search terms table, read the first 2 rows.
So it forcefully injects the number 2 into the current context, completely overriding the user's explicit request for 3.
Yes. It can't comprehend variables at all. It's just blind copying.
But Mem-pi works differently.
Exactly. Mem-pi is a parametric memory. That means its knowledge isn't stored as raw text. It's baked into the mathematical weights of its neural network.
Right.
So Mem-pi looks at the abstract lessons of the past experience, looks at the current prompt, dynamically processes the number 3 as a variable, and rewrites the hint on the fly.
It adapts.
Yes. It tells the agent, take the first 3 rows. It adapts the memory to fit the exact parameters of the present moment.
It resolves the mismatch through active computation rather than just copying stored examples.
It's just so much smarter.
It is. And it's also worth noting that they took this a step further by testing a multimodal version of Mem-pi. In environments like web navigation, the agent isn't just reading HTML text, right? It needs to understand the spatial layout of the screen.
Right, like where the buttons actually are, how the drop-down menus overlay each other, that sort of thing.
Exactly. When they fed visual observations, actual screenshots of the browser into the memory model, utilizing a vision language backbone, they saw consistent performance bumps.
Visual context really helps.
It does, especially in highly visual domains like the content management system and shopping tasks. Adding vision resulted in an overall 2.7 percentage point increase in success. The visual context helped ground the generated memory, making the hints far more accurate to the user interface.
Here's where it gets really interesting, though.
Oh, yeah.
You would logically think that to achieve a 50% performance boost on complex web tasks, the AI must be doing significantly more work.
That would make sense, yeah.
You'd assume it's pumping out massive, highly complex hints to micromanage the agent. But that leads us to the efficiency paradox of Mem-pi.
The efficiency paradox.
Yeah, Mem-pi achieves these massive performance gains while using 31% fewer memory tokens per task than the earlier stages of its own training.
That is a staggering statistic.
Yeah.
I mean, it is feeding 31% less data to the agent, yet achieving significantly higher success rates.
So how is it possibly doing more with less?
It all comes back to the abstain token. By analyzing the rollout data, the researchers found a direct correlation between task difficulty and the abstention rate.
Oh, interesting.
Yeah, on the easiest tasks, the ones the base agent already possessed the skills to solve perfectly on its own,
Yeah.
Mem-pi abstained almost 71% of the time.
71%.
Right. But on the hardest, most complex tasks, its abstention rate dropped to around 13%.
It quite literally learned to read the room.
Exactly. It proved that always generating memory is fundamentally inefficient and actively counterproductive. Unnecessary memory just adds cognitive noise to an already solvable task.
It's distracting.
Exactly. By only using tokens when the task is genuinely difficult, Mem-pi dramatically reduces the computational overhead and provides a much cleaner, distraction-free environment for the agent to execute its logic.
So what does this all mean for you, the listener, and for the future of the tools you use every day? Let's zoom out a bit.
Good idea.
We are witnessing a fundamental paradigm shift in artificial intelligence. We're moving away from treating AI memory as an external hard drive, a dusty filing cabinet where you retrieve outdated text files.
Thank goodness for that.
Right. Instead, memory is becoming a generative policy. It is acting much more like a true cognitive process. It synthesizes context, adapts old rules to fit new variables, and perhaps most importantly, it possesses the self-awareness to know precisely when to stay silent and let the agent do its work.
It's a massive leap toward artificial systems that actually exhibit judgment rather than just recall.
Judgment is exactly the right word.
But if we project this trajectory forward, it raises an incredibly profound question.
What's that?
Well, if AI memory is no longer just an objective, copy-pasted transcript of the past, but instead a synthesized, generative interpretation that actively adapts and changes over time,
Okay.
will future AI systems eventually develop their own uniquely tailored subjective memories based on their specific interactions?
Oh, wow.
And if so, does that mean our personal AI assistants are about to develop distinct, localized personalities, shaped entirely by their uniquely subjective, generative reflections of their lived experiences with us?
That actually gives me chills. The idea that your AI won't just remember what you're asked it to do, but will dynamically shape how it thinks about you based on its own internal evolving interpretations.
It's wild to think about.
That is no longer just a tool. That's a dynamic relationship. It's a completely different frontier for how we interact with technology. And on that note, we're going to wrap up today's deep dive. Keep questioning the systems you use, and we'll see you next time.